Okay, crystal field theory of our coordination complexes. So this theory, it's pretty nice. It's quite straightforward, more straightforward maybe and easier to understand than ligand field theory. Because it doesn't really like look too much detail at the orbital structure of the ligands. It kind of just treats them as hard spheres because that works really well for crystal structures, which is why it's called crystal field theory, because it was developed to understand the structure of crystals. It does work for other systems that might be like, for example, in solution phase or something like that. But that's its limitations really, is the way that it treats ligands. But for the people who created it, who wanted to understand crystals, it worked perfectly well for them. So this theory kind of looks specifically at the different d orbitals on the central metal. And so this is probably for the first time where we have to kind of actually try and understand and remember the structures of the d orbitals, because it's going to be important to try and understand why certain orbitals energies are changed based on their interactions with ligands. So here we have our bonding axes. Here we have our different d orbitals. We've got our dx squared minus y squared, dx squared minus y squared because the orbitals lie along the x and the y axes, dz squared because the primary axis of the orbital is along the z axis, dxy, it kind of lies in between the x and the y axes, dz, xz, sorry, lies between x and the along the z axis, but sort of like between the x and the z, and then the dyz, same thing, sort of lies along the plane of the y axis and the z axis. And so these are sort of the constant electron density surfaces of the 3D orbitals. So the first set of d orbitals that we have. So yeah, potential to pretty much know them. We can see here where the nodes are for the dyz, dxz, and dxy orbitals. That the nodes are kind of where these planes are drawn, where there's limited or no electron density. So the shapes and orientations of d orbitals. So the key points here are 5 of them. So we've got dz squared, dx squared minus y squared, dxy, dxz, and dyz. And so their orientations or axes correspond to their labels. The shaded, unshaded regions are labeled plus or minus, or red and blue, or green and blue, or somehow they should be differentiated from each other. We'll donate regions where the sign of the wave function is either positive or negative, or in phase or out of phase. Basically, there's some differences between the different lobes, and that's something that would mean that the colors do have a meaning. So it's really arbitrary in which way the lobes are labeled. So for example, black this way and white this way is the same as black this way and white that way. It doesn't really matter, it's perfectly fine. But the symmetry does need to be correct. So for example, here and here, the symmetries are incorrect. So it should be, the same color should be opposite each other. On passing through the nucleus in a straight line, the sign of the wave function will not change. The orbitals are said to be Goradic. So like that's what this is. So that's why this side and this side have to be the same, because whenever you pass from here to here in a straight line, the sign of the wave function should not change. And from here to here, it's the same thing. Across here, across here. Whereas with the p orbitals, they do change as you pass through the nucleus. And so we have a node there. And so yeah, you need it's going to be useful to be able to draw the d orbitals. And also to be able to rotate them in your head and sort of think, well, okay, so my xz is kind of in between the x-axis and the z-axis. So any ligands which are approach in that direction are going to interact with that orbital. Is that interaction going to be favorable or unfavorable? Those sorts of things. And so you can see that as we go through. Extending crystal field theory. So crystal field theory is obviously based on the assumption that ligands can be treated as simple points of negative charge, which repel electrons in the d orbitals. This predicts the d orbital energies for various geometry and helps explain color, magnetism, stabilities, etc. And see also, like we talked about that during the first coordination chemistry lecture. Like this, so what we're going to find out here as we go through this is that the different orbitals will interact with the ligands in different ways. So whenever you have an octahedral complex, obviously you have 6 ligands which approach from different directions. They're all 90 degrees to each other, but ultimately the position of the ligands there have different overlaps with the available d orbitals. So the different overlaps are going to result in different effects on the energy. So in crystal field theory, it's just assumed that the ligands are sort of infinitely small points of negative charge, which will sort of repel any electrons which are in d orbitals. And so if there is a significant amount of overlap with the d orbital, then they're going to repel more. And if there's less of an overlap, they're going to repel less. And so that's going to have an effect either stabilizing or destabilizing on the d orbitals. So how does this work? So the metal ion is first imagined to be surrounded by a perfectly spherical shell of negative charge. So we have here our metal, central metal, and then around it we have our different ligands, which are represented by these black lines. And then we assume that this metal with its 6 different approach vectors is surrounded by a sphere of negative charge. And so this repels the electrons in the d orbitals, which results in the d orbitals increasing in energy. So from the kind of totally degenerate case of the gas phase metal ion, and now that we are seeing an increase in, or seeing this effect of the ligands, it sort of destabilizes the metal in general. And so all of those orbitals will increase in energy. So we go from, the 5d orbitals at the gas phase. So it's just going to gas phase, I'm going to write G. Then if I bring it in, so that would be this one, that would be the gas phase one side, gas. And then this would be our, we see that there is an increase in energy if this is the energy. E. There's an increase in energy on the addition of this sphere of negative charge. They're still, though, degenerate, like the orbitals still, they've all increased in their energy, but and being destabilized by the presence of this sphere of negative charge, but they're all experiencing the same amount of negative charge, which means that they're all still degenerate. And it can be shown that they all increase with the same amount, and so they remain degenerate. So this is basically what I was talking about. So we've got the metal ion in the gas phase without this sphere of negative charge, with its 6 potential approach vectors. And so this has the potential energy which is lower than the case where it is surrounded by this negative charge. So that increases the energy. However, the orbitals are still degenerate. So then to mimic the effect of the ligands, since obviously the ligands have different approach vectors, they're along these octahedral lines. They don't totally express themselves equally over the whole surface of the metal. They're much more localized than that. We have to imagine or sort of like match up where the ligands are compared to the metal orbitals, the d orbitals. So to mimic the effect of ligands, we now imagine that the shell of negative charge is concentrated at certain points. For an octahedral complex, this corresponds to the 6 points on the Cartesian axis. So we've got the Z top and bottom, X right and left, and Y front and back. So in this arrangement, d orbitals are affected differently depending on their orientation. So you can see that, for example, the dz squared orbital, which would lie along this plane, is going to overlap with these ligands here and here. Any orbital, like the x squared minus y squared, is going to overlap here and here, here and here along the x and the y axes. The xy orbital will also lie sort of here, 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 and here in between the x and the y axes, which will also have a somewhat significant overlap with ligands along those axes. So you can see here the d orbitals with the octahedral polygon drawn over them, which indicates the position of the different orbital or different ligands. So for example, the dx squared and the dx squared minus y squared, these all point directly at the ligands, so the net points of negative charge, which means that these are going to have the most repulsion with the ligands, which means that they're going to be increased in energy, higher in energy. Whereas the dxy, dxz, and dyz all kind of point in between the ligands, which results in less repulsion because the repulsion is not, it's not direct end on, but rather sort of like glancing. And so this means that they actually get slightly stabilized compared to the sphere model that we had seen previously. So this is how it looks. So obviously we saw this part on the left first. We saw the free metal ion with its relatively low potential energy, 5 degenerate orbitals. Then when we applied this sphere of negative charge, we saw that it increased the energy of the 5d orbitals, but they still remained degenerate because the influence of the electron density of the ligands was expressed equally over the surface of the metal, which meant that they still remained degenerate. Then whenever we change that to be a more realistic view of the potential energy of the different orbitals with respect to the ligand positions, we saw that the ligands positioned themselves along the Cartesian axes, and this localized that negative charge and that repulsion effect with the central metal. So the ligands which kind of like are end on are the ones which are going to be the ones that kind of experience the most repulsion. So like the dz squared obviously points along here and here, so that's directly in line with those ligands. And then the dx squared and minus y squared, that points along the x-axis and the y-axis, which means that they experience a direct repulsion between the ligand and those orbitals. Whereas the other three, and at least in an octahedral complex, they experience sort of glancing repulsion. So the repulsion is not direct, which means that ultimately we have a kind of a little bit of a reduction in the kind of repulsion effect, which means that ultimately those end up being slightly stabilized compared to this sphere of negative charge. And so the distance or difference between these has an energy associated with it. And it's called the octahedral splitting energy. So this delta O. This delta O can actually be determined experimentally using like things like absorption spectroscopy. So UV vis spectroscopy can even show us the value for this. So it creates for us this octahedral splitting diagram where we have an EG set and a T2G set. So these are the symmetry labels for these orbitals. So the dz squared and the dx squared minus y squared, they're EG sets, and the dxy, dz, xz, and dyz are the T2G sets. So always whenever you're drawing these out, you need to label these three orbitals, the T2G set, and these two as the EG set. You don't necessarily need to indicate which d orbitals they are. You must always indicate the symmetry. And then you must also realize that this is the line, this line, dashed line represents the spherical case. And so the T2G set is going to be stabilized by 0.4 of the total delta O energy, and the EG set are going to be destabilized by 0.6 of the total delta O. So if this was like, I don't know, 1,000 wave numbers, then this would be 0.6 of that, so it would be 600 wave numbers, something like that. Crystal field theory, valence shell electron repulsion theory does not predict the shape of transition metal complexes because we've got two complexes here which both have 4 electron domains, but they have different structures. And we also saw that the valence bond theory or hybridization for bonding and transition metals is not good enough. It fails to rationalize structure. It fails to explain color. It fails to explain the bonding of carbonyls. And it fails to explain many magnetic properties. So that was why the better system, the crystal field theory, was developed. First devised in the 1930s, but only later accepted in the 1950s. So crystal field theory is semi-quantitative. It's got the splitting diagram. It describes the bonding pretty well, the magnetic properties, and in some cases the spectra, color of transition metal complexes. It's an electrostatic theory, so ligands I thought of as point charges surrounding the positive metal ion. So it's effectively an ionic model. It doesn't really consider that there could be sharing of those electrons in somewhat covalent bonds. It's very good for the octahedral case, but then it struggles for other structures, although it still works pretty well for structures like square planar, tetrahedral, and so on. But it works best for octahedral. It assumes that the ligands only approach along the axes, which means that it has the biggest effect on the orbitals which lie along the axis. So here is a look at how, if we have a free metal ion, then we have one with ligands, but the ligands all project equally onto the orbitals. This would of the D metal line up with the ligand approach vectors, then we can create this crystal field splitting in an octahedral field diagram. So as I said before, this is kind of how you would draw out one of these octahedral field splitting diagrams. You would also have to label, however, the T2G set and the EG set. So the EG set is composed of the dz squared and the dx squared minus y squared, which both lie along the approach of the ligands. The T2G set are composed of dxy, dyz, and dxz. The average energy of the d orbitals after crystal field splitting remains the same as for the hypothetical spherical case. The increase in energy of the approach of the ligands is more than compensated by the increase in bonding between M plus and L minus. So delta O, e.g. T2G. Yeah. So you always want to make sure that you label these two at the top as the EG and these three at the bottom as the T2G set. These are their symmetry labels. Okay, so then with our splitting diagram for the octahedral system, we have this point here, which is called the barycenter, which would be the average energy level in the spherical situation, i.e. all the orbitals behave the same. So that was where we had this like sphere of negative charge applied equally across all of the metal center. So usually whenever you would draw this out, I would expect to see at least this much information. You don't need to include these. That's not really necessary. That's already understood. So you have like 2 orbitals at the top, 3 at the bottom. Then you would have this barycenter, which would be closer to those at the bottom. It doesn't need to be exactly like 0.4 and 0.6, but you need to indicate that you know that this is 0.6 going here and this is 0.4 going down, and then it's 0.4 delta O, and it's 0.6 delta O, and then this is total is delta O. And then later on, you could fill in electrons if you knew what the metal was. But in the simple case, this is enough. Okay. So let's take a look at some actual examples. So we introduce electrons into the lowest possible orbital, of course. And so this is how we start to understand why in our magnetism that we saw in the previous part, how we could have, we thought we had a certain number of unpaired electrons, but it turns out we had something totally different. So let's have a look at our octahedral splitting diagram here, where we have D1. So we put this is our hexa aqua titanium 3. So we put 1 electron in there. The complex then is going to be 0.4 delta O, more stable than we thought it should have been. And this is because the electron has gone into an orbital which is lower in energy than the spherical case. And so this is called the crystal field stabilization energy, CFSE. So sometimes you might be asked to calculate this CFSE based on based on the electron configuration of the metal. There is an analogous version for ligand field theory called ligand field stabilization energy, or LFSE. Calculations pretty much done the same. This diagram is pretty much the same for ligand field theory as it is for crystal field theory. Actually, not pretty much, it is the same. So except, for example, here, calculations of the different crystal field stabilization energies. So we have D2, D3, D4, and so on. So if we've got D2, we have crystal field stabilization energy of 0.8 because it's 0.4 plus 0.4 gives us 0.8. Here it's 0.4 plus 0.4 plus 0.4, that gives us 1.2. Here with D4, we have 0.6 because we have 0.4 plus 0.4 plus 0.4 is 1.2. But then we subtract this destabilization effect of the 0.6. And so this is for the D4 high spin case, which is an effect of the ligands, which are classified kind of based on whether they are high spin ligands or low spin ligands, which we'll discuss as we go through. But basically with a high spin complex, it means that this total energy of delta O is quite small. So for example, see here, the distance between there, delta O, and then here, delta O, the difference is much larger. So that means it's harder to put electrons in this case. And so we find out that the stabilization energy here is 1.6 for a low spin complex. The reason why it's called low spin is because there's only 2 unpaired electrons, whereas here there are 4. And so typically this is from weak field ligands, and then this is from strong field ligands. So crystal field splitting and stabilization energies. So how big is delta O? So the visible spectrum titanium or hexa aqua titanium 3 in aqueous solution is shown here, where we have different peaks. We've got probably a shoulder here, a peak here. So this is caused by the absorption of UV light by the electron in the T2G set. And then this absorption causes an excitation from this T2G set into the EG set. And then obviously we know what wavelength that happened at. And so if we know that, or the wave number that it happened at, if we know that, and since we know the how much energy one wave number is, we can actually calculate the energy of this transition by multiplying the wave numbers by this joules per mole. We get we see there's 243 kilojoules per mole of energy in this transition. So, or at least the splitting of delta O is 243 kilojoules per mole, which is similar to an average single covalent bond. How can we measure these values? So it's like I said before, we can measure it using UV-vis spectroscopy. If you can make an aqueous solution of these, or well, a solution in any kind of a solvent, really, you can measure these pretty easily, as long as they're within the range of your spectrometer. It's not a difficult measurement to do. You get some sort of lambda max or a wave number max in this case, and then that corresponds to the energy gap between the T2G and the EG set. But of course, like it's going to change based on which complex you have. Not all complexes are going to absorb at the same wave number. So for example, here, this titanium complex around 20,300 wave numbers give a purple color, but other complexes may absorb in the UV, which means that they might be colorless. D block elements are often colored because their transitions between the T2G set and the EG set are often fall within the visible range. So the blue crystals of copper 2 sulfate dissolve in water to give a pale blue solution of hexa aqua copper 2, but the solution must be very concentrated before the color qualifies for being intense. Intensity measured by molar extinction coefficients, but the color depends on the metal ion. So potential different colors for the metals. So for example, our titanium 3 plus might be purple, vanadium 3 plus might be green, zinc 2 plus is colorless. The transition falls in the UV range because remember our zinc 2 plus has 10 d electrons, so all of those d orbitals are filled. So any transitions which actually occur are going to be outside of the visible range. They're not going to be covered by this EG or T2G to EG transition. Whereas the others, they all have at least one vacancy in their orbitals, especially in the EG set. So it means it can be excited, and if there is a potential absorption and transition between the T2G set and the EG set, we are definitely going to see a color. The color depends on the ligand. So for example, all of these are cobalt 2 plus metals, but they have different ligands, and that changes the color. Now you don't need to remember what all these colors are. You just need to know that the colors change based on what metal it is, even if the ligand stays the same, or if the metal stays the same, then the effect of the ligand is going to be what changes the color. Can even like the metals, different oxidation states of the metals can have different colors as well. Because whenever you change the oxidation state, you're changing the number of electrons. You're changing the number of electrons, then you're potentially also influencing that crystal field stabilization energy, which results in a slight change in the energies of the orbitals. Not a huge change, but maybe enough to change the color and the wavelength of that absorption. There are, of course, some problems. If the d orbitals are degenerate, there's going to be no electronic transitions, and many d-d transitions are not allowed. So this is due to the Laporte selection rule. So this is coming back to quantum mechanics. Electrons can only be excited when the delta L must be plus or minus 1. And so for many 3D transitions, delta L is, of course, going to be 0. And the consequence is that many compounds are not strongly colored unless we really concentrate them a lot. But ultimately, it's not really anything to do with the color, just sort of the intensity. So the more of them that we have, the more strongly colored it is. And ultimately, with a lot of these rules, as I'm sure you're aware, there's a lot of exceptions to the rules. So like even though the transition is forbidden, we still observe colors. So what affects the size of this splitting energy, this delta, i.e. the color? The oxidation state of the metal center, so it's something that I said. So delta increases with oxidation state, the charge of the metal. So the higher the oxidation state, the larger the splitting energy. The d orbitals involved, so crystal field splitting energy is going to be smallest for 3D and largest for 5D. So for chromium to molybdenum or cobalt to rhodium, there's a 50% increase in delta O. And then from rhodium to iridium, there's a 25% increase in delta O. So this is going from 3 to 4, and this is going from 4 to 5. So typically the biggest change in all transition metal properties is observed between the 3rd or 3D and the 4D. So going from 3D to 4D has the largest change. 4D to 5D, typically not that big of a change. 4D and 5D metals typically have, if they're in the same triad, they'll have much more similar properties than 3D metals. So 3D is the strangest, or it's the most different, and then 4D, 5D often a little bit similar. So as a rule of thumb, 2nd and 3rd row octahedral transition metal complexes are low spin as a consequence of this. So how does that work? Well, low spin is whenever there's a large splitting energy, and the reason why low spin causes, why this splitting energy, the size of the splitting energy affects the spin, it's because if the splitting energy is very large, then it's harder to put electrons in those higher energy orbitals because it just destabilizes the complex a lot more, and so it becomes easier just to put it in the T2G set. And if you're pairing electrons, you're reducing the number of unpaired electrons. If you reduce the number of unpaired electrons, then you're reducing the spin. The number and geometry of the ligand, so the crystal field splitting for the approach of 4 ligands will be weaker than for 6 ligands. So why is this? Well, if you've got 4 ligands, you only have 4 points of negative charge as opposed to 6 ligands where you have 6 points of negative charge. So you reduce the number of ligands, you reduce the amount of repulsion, you reduce the amount of repulsion, you reduce the increase in energy. Okay. So the nature of the ligand, so it has been shown experimentally that the crystal field splitting ability of the ligands towards most transition metals follows the approximate order here, where we have the free metal ion shown here. And if we have weak field ligands, so this is really as complicated as crystal field splitting energy or crystal field theory gets with ligands, is looking at whether a ligand is weak field or strong field. It doesn't really try to understand, if I have oxygen substituents versus fluorine substituents or something like that on my ligand. It just really looks at them and classifies them broadly as weak or strong field ligands. So strong field ligands will create low spin complexes because the splitting energy becomes very large. And so it's easier to pair the electrons, or there's a better energetic, it's more energetically favorable to pair the electrons. Whereas here in a weak field, the splitting energy is a lot smaller than the strong field. And so it becomes possible to put electrons in the EG set. So this is kind of the order of the ligands. So we have weak field ligands here where there's a small splitting. So these are high spin, weak field is high spin. So things like iodide, bromide, thiocyanate, chloride, fluoride, and so on. Whereas strong field ligands create a large splitting, things like carbonyls or cyanides and so on. Things like water are typically kind of relatively neutral. The isothiocyanate is more of a strong field ligand than the thiocyanate. So if it binds through the S, it's going to be, which is somewhat softer than the N, it's going to be more on the weak field. But that's not, like the hard soft acid base theory does not really predict very well if it's a weak field or strong field. I mean, look, there's fluoride here is a relatively weak field ligand, but it's a very hard base. So this is called the spectrochemical series. A spectrochemical series because obviously the nature of the ligand will change the color of the complex. And so colors and things like that are related with wavelengths and those transitions. And so those are colors, and that's part of spectroscopy. Okay. So high spin versus low spin. Electrons occupy degenerate orbitals singly with parallel spins. This is from Hund's rule. So we fill up degenerate orbitals one by one until they all are at least half filled. So we can see here the D1, D2, and D3. We fill, like, this is pretty much the same for high and low spin. The first three electrons will always go into the T2G set. So one electron in T2G set, D2 is 2 electrons, and D3 is 3 electrons in the T2G set. So the fourth electron, however, has a choice. It can either go into the EG set, or it can pair with one of the electrons in the T2G set. So for example, if I have a high spin, which is going to be weak field, so if I've got a ligand like iodide or something like that, I would have a high spin complex. So the splitting energy is going to be quite small, and so the electron will go into the EG set. So I have T2G3, EG1. So 1 electron in the EG and 3 in the T2G. This would be the high spin case. Whereas if I have like a strong field ligand, like a carbonyl, then I'm going to have a big delta O. And so I'm going to see that the electrons instead get paired because the destabilization effect of putting into the EG set is too great. And so it's going to have to go into the T2G set. So whether or not it goes into the T2G or the EG set depends on the size of delta O versus P. P is the pairing energy. So this is the repulsion between 2 electrons in the same orbitals. This is electrostatic forces. So whenever delta O is larger than P, we're going to have a low spin complex. But whenever delta O is smaller than P, then we have a high spin complex. So yeah, the repulsion from the electrons is larger than the splitting energy. So that means we would have a high spin complex. Crystal field stabilization energy. So consider an octahedral D1 ion. We have here the degenerate orbitals that's a spherical case, and then we have them split here and here. And so relative to the spherical shell model, it is stabilized by 0.4 delta O. So it's stabilized. So compared to here, it's stabilized here. So for titanium or hexa aqua titanium 3, the crystal field stabilization energy is 97 kilojoules per mole. The D5 ion, however, it has no crystal field stabilization. So this is the high spin case where we have 5 unpaired electrons. So if we calculate the crystal field splitting energy, we see that it's 0.4 times 3. 0.4 is these 3 electrons here, minus 0.6 times 2, which are these 2, gives a total of 0. So it would be 0.4 times 3 is 1.2, 0.6 times 2 is 1.2. So 1.2 minus 1.2 gives us 0. So there's equal stabilization and destabilization. So there is no crystal field stabilization energy. So it is not stabilized compared to the spherical case, which is possible. So for high spin octahedral complexes, so high spin typically will have the most unpaired electrons, at least compared to things like low spin complexes. And so you can just see here that the different D electron counts and then their crystal field stabilization energies. So for example, D8 in a high spin case would have, let's see if I can draw it out. So it's got the, so there's the barycenter. So the splitting diagram. It looks something like this. Yours will look neater, of course, because you won't be using a mouse pad. Okay, so if I'm looking at D8, it shows the one which has the most electrons, of course. So first of all, we fill them up according to Hund's rule individually, because this is a high spin case. So we will get unpaired electrons or electrons filling into the EG set, which is this one, and then T2G. And then this is obviously 0.4 delta O. So fill in, so it's 5 electrons so far, and go back down to the bottom, 6, 7, 8. Okay, so that's our D8 case, D8, high spin case. All right, so then we can calculate the crystal field stabilization energy. So that's going to be equal to the number of electrons in the T2G set times 0.4 delta O. So should be 0.4. Sorry, I wrote the wrong way around. And then this one here is 0.6 delta O. Okay. So those in the T2G set, so that's 1, 2, 3, 4, 5, 6. So 6 times 0.4 minus 0. Times 2 times 0.6 is going to be equal to, so 6 times 0.4 is 2.4 minus 1.2 gives us this 1.2 here. I encourage you maybe just to do similar calculations and diagrams for the others, just to sort of practice. So high spin or low spin, so Hund's rule, so that's obviously where electrons will generally remain unpaired, but only if the energy gain from crystal field stabilization energy is insufficient to overcome the repulsive interaction of 2 electrons occupying the same orbital. So if that repulsive force is too large, or at least is larger than the crystal field stabilization energy, then what we will see is that the electrons will remain unpaired. So because of crystal field stabilization energy, electrons will occupy the lower energy T2G orbitals. So delta O is going to be less than the pairing energy. So that will give us weak field or high spin. Whereas when delta O is larger than P, we will have strong field or low spin. And so this explains the number of unpaired electrons in all octahedral complexes. Crystal field stabilization energies for different metal ions and octahedral complexes. So the number of electrons in T2G set, the number of electrons in EG set, crystal field stabilization energy, or delta O, and the number of unpaired electrons for weak field and strong field cases. So note the parameterization of the ligands affects the size of delta O and leads from crystal field theory to ligand field theory. So the ligand effect. So this is kind of where we're doing a more robust treatment of the ligands. Will be in ligand field theory. So far we've looked at octahedral geometries in particular and the resulting delta O. But there are other coordination geometries, each with their own splitting pattern and energy gap. And so this accounts for which geometry is adopted, which gives the lowest energy level from crystal field splitting energy. So other geometries that we can do using this theory are tetrahedral, square planar, trigonal planar, and trigonal bipyramidal. So how does square planar differ? So it's basically the same as octahedral. You just really removed two of the ligands. So if we remove the ligands along the z-axis, then we'll just have the ligands which are in the plane of the x and y axes. So there's these here, which means that hopefully you'll notice or realize that if we remove the ligands along the z-axis, that means we've removed that repulsion with the dz squared orbital, which means the dz squared orbital will actually reduce in energy. It'll be more stable because it's not repelling any electron density from ligands. So the highest energy orbital then will become the dx squared minus y squared, that orbital which points directly along the x and y bonding axis. So here we have the octahedral case and how things change. So for example, if we elongated the bonds on the z-axis, we would see that the repulsion of the dz squared and the ligands would reduce, and so that would reduce this energy here. But we would also see that because we're lengthening these bonds, typically the other ones are pulled closer, which would obviously reduce or would increase the repulsion, increasing also the energy. And if we continue to do that until such cases as we removed those ligands, we would see that we would continue along that path where the dz squared becomes even more stable because, well, there's now no repulsion. Here there's a little bit of repulsion, but here there's no repulsion really at all. And so that greatly stabilizes that orbital. However, the orbitals which lie along the x and y axes, so the dx squared minus y squared, the one that is directly along these bonding axes, is going to be very much more stabilized than the octahedral case, because when we remove the ligands along the z-axis, it pulls or shortens all of these bonds. And so if those bonds get shorter, then that means that the repulsion of between the ligand and the orbital is increased, which increases the energy of those orbitals. So the x squared minus y squared and the dxy become the most destabilized, the highest in energy. And so the delta then for square planar, so delta square planar, is going to be between these orbitals. And then the others are much more stable. And notice also that the symmetry labels for these have changed. It's no longer EG and T2G, but now EG, A1G, B2G, and B1G. So the results here is the orbital with Z character is lowered in energy, and those with XY character are increased in energy. The resulting splitting diagram has one very high energy orbital, which is the dx squared minus y squared, and four relatively low energy orbitals. And so the delta O, or delta square planar, or the splitting energy, is going to be between this dx squared minus y squared and the dxy orbital. Tetrahedral case then. So these are a little bit more difficult to relate to the Cartesian axes or the orbitals. However, it is possible to do it. It just means that a lot of the repulsion is not going to be direct with the d metal orbitals. A lot of it is going to be kind of glancing or sideways on or something like that. But ultimately what happens is that it's effectively the inverse of the octahedral case, where the total splitting energy becomes less than half because of this lack of direct repulsive force. So it's easiest if you invoke the cube relationship. So like you put the ligands on the corners of the cube, and then the axes point through the faces, and then you can see where the ligands are at alternative corners, and then put back in the axes, and you'll be able to see where the most overlap with the orbitals will be, and therefore where the greatest repulsion will be. So we now see that dz squared and dx squared minus y squared point at the centers of faces. So dxy, dxz, and dyz point at midpoints of the edges. And so these are kind of going to be the highest energy. Whereas these two orbitals kind of just point in between. So whereas in the octahedral case, the dxy, dxz, and dyz kind of pointed between the ligands, now that's the dx squared minus y squared and the dz squared orbitals. They kind of point between the orbitals or between the ligands, which means that they become more stabilized, and the dxy, dxz, and dyz now point and have a little bit of repulsion with the ligand. So you can see that this orbital kind of repels here, and this one kind of repels here. And then obviously we've got similar effects going on here and here, which results in these ligands becoming destabilized or higher in energy. But there are ultimately no orbitals which point directly at the ligands, but these three are the closest. And then the octahedral, so it's going to be less, the splitting energy is going to be less than in the octahedral case. So this is the tetrahedral splitting diagram. So it basically becomes the delta tetrahedral, the T2 and the EG sets are inversed. So generally the delta tetrahedral is equal to 4/9 of the octahedral splitting energy. And so you can assume that tetrahedral complexes only exist in weak field or high spin configurations. Why? Well, I mean, if it's 0.4/9 of the delta O, then it's going to be much smaller. It's smaller because fewer ligands, 4 versus 6, and no orbitals point directly at them. Okay, so square planar or tetrahedral. So this question generally pops up whenever you're dealing with a D8 species. And so the larger the value of the splitting energy, the more the possibility for the square planar complex. This is because of the arrangement of the electrons. I mean, both of these are 4 ligand complexes. So whenever we have a large value for delta, we see that the electrons are more likely to be paired, which leads to a higher likelihood for a square planar complex. So some math rule of thumb, so for a tetrahedral D8 complex, we see that there's minus 0.8 delta crystal field splitting energy, whereas for a square planar, it's minus 2.46 delta crystal field splitting energy, which means that we expect the square planar to be much more stable than the tetrahedral. And so therefore, if it's more stable, it's probably more likely, unless there's some other thing which is influencing the structure, like ligands or the sterics. So the tetrahedral would have 2 unpaired electrons, the square planar would have no unpaired electrons. And so the energy is required to pair these electrons, so the pairing energy. So if the difference between the tetrahedral and square planar crystal field splitting energy is greater than the pairing energy, then it's going to be square planar. But if the difference is less than the pairing energy, then it's going to be tetrahedral, because tetrahedral results in less pairs of electrons. So the consequences here are that for second and third row D8 complexes, they form square planar complexes. And in first row D8 complexes, they're typically with weak field ligands, they're tetrahedral, but with strong field ligands, they're going to be square planar. So remember that weak field ligands reduce the delta crystal field splitting energy, whereas strong field ligands increase the delta. Geometric effects of crystal field splitting energy. So compare crystal field splitting energy for competing geometries. So make sure to work in consistent values. So for example, delta O, don't mix up delta O and delta T, because you'll end up with some confusion. So prediction is the D1 to D4 all prefer octahedral rather than tetrahedral geometries. D3 is the most, prefers octahedral the most. D5 has no electronic preference for any geometry. The reality, however, is that D3, so for example, chromium 3+ is always octahedral. D5, manganese 2+ and iron 3+ will both form octahedral and tetrahedral complexes. So for example, we have there tetrabromomanganate and tetrachloroferrate. So if low spin D6, it should favor octahedral geometry. So it's the geometric effects of crystal field splitting energy occurs for the first row with strong field ligands. So for example, the hexacyanoferrate Second and third rows, they're almost always octahedral. They don't really like to have other geometries. So the delta increases the most from first to second, and then less from second to third, but still generally increases because the d orbitals get larger, so there's going to be a greater interaction with the ligands. D8 then, tetrahedral versus square planar. This is kind of just another version of what we talked about a moment ago. So generally D8 strongly prefers square planar, but of course we must compare that to the pairing energy. Nickel is finely balanced, depends on the ligands really, depends on whether sterics win. So this is something that I said. So generally this would probably want to be square planar. However, because of the bulkiness of these ligands, it's not possible. At least not in this case. So the steric hindrance wins, but here in this case, the electronics win when it comes to square planar. Square planar complexes, so palladium 2, platinum 2, and gold 3 are always square planar, even with bulky ligands. This is because the electronics win, because the delta increases from first to second to third row of the D block. So for D10, the crystal field splitting energy is equal to 0 for any geometry, and the geometry is determined by sterics. Other geometries are here. We won't really, this is just really more for reference. Square planar, sure, but the others like trigonal planar, trigonal bipyramidal, and trigonal prism. I won't ask you to draw these diagrams, but it is still the same sort of principle, the same sort of how do the ligands line up? Do they overlap with the orbitals? And is it going to be a significant amount of overlap? So for example, the trigonal bipyramidal, what do you call this? The ligands which approach along the plane of the trigonal planar part do not point along any of the Cartesian axes directly. And so that means that the repulsion of the, for example, dx squared minus y squared is going to be reduced. But they have the most overlap, the dx squared minus y squared and the dxy. And so that means they're going to be less destabilized or less stabilized than, for example, the dx and dy set, which have very poor overlap with those ligands. Okay. And so that will do us for this part. Then the next time we'll talk about some of the more complexities of this system. So thank you.